So here is our system of equations with y1s and y2s. All right. So what we're going to do is take a look at a few different files here. We're going to look at Pendulum DE. So this is our idea of the calculation of the pendulum differential equation. And the idea is it's supposed to be as close a model to what we have on the page as possible. So on the page, I'm going to look at the right-hand side. These are our inputs, or this is going to involve the input. On this list are y2, there's a g, there's an l, there's a mu, and there's a y2. So to be able to calculate my derivatives, which are the left-hand side, and they're my output, I need to have all these variables here. Now, if you look at the input for this function here, you'll see almost that same list. You see y, mu, and l. Y, mu, well, mu and l are good. G, I don't bother inputting because we're going to wire it because we're not expecting to change the place where we're doing this, which is on Earth. So G's taken care of. Sorry, there should be a y1 here. A y1 and y2. Why do we only have one y input into this function here when we need two y values? How could we package our y values so we only have to handle one thing in MATLAB, but it actually has two values in it? How would we represent that thing? As a vector, exactly. Because, in fact, I can't express how exciting this is. The notation, if y is a vector of two things, of y1 and y2 in MATLAB, then y bracket 1 in MATLAB is going to be exactly the same thing as y sub 1 in our math. It's going to look like what we want. MATLAB, y the first element, that's the first element of some vector, is what we mean by y sub 1. And this is going to make life easy when we look at our equation now. We've got all the inputs covered. And, hey, look, the derivative of y1, so we make a new vector that's going to be our output. It is equal to y2. That's exactly this sentence here. The derivative of y1, and notice we're going to have an output vector. This vector here is going to be dy dt, which is going to have the derivative of the first thing, first variable in its first slot, and the derivative of the second variable y in its second slot. And we just literally convert everything over. Minus g over l sine of y1. Minus g over l times sine of y bracket 1. Oops, without deleting it. And minus mu times y of 2. So this, when you create these differential equations, and we'll be doing that again before the end of the week, we translate the math into MATLAB. We do not do anything. We just say, here's the rule. It has to be in this new multivariate form with single derivatives, but otherwise we just take what's on the page and convert it to MATLAB. That's it. And the idea is that anybody could come along now and give us our current, remember what y is going to be. It's got our current angle and angular velocity. They can hand us that, the friction coefficient and the size of the pendulum, and we can calculate at any point then the velocity or the rates of change of y1 and y2, which is the rates of change of our position and velocity. That's what we get out of this. We know where we are. We can find out the rate of change. That's the way to think of these differential equations. Now we're going to take a look at the script 8.2. Okay? So this is going to have some familiar ingredients based on last class. We're going to define our friction coefficient. We're going to define the length of the pendulum. And we're going to define our differential equation as a function of t and y. The MATLAB solver only works with functions of t and y, so we make a function that's a function of t and y. Notice all it does, though, it's just a renaming of the pendulum, which has mu and l defined earlier, hardwired, and it's just going to pass. What this is going to do is be a function that'll take in two numbers, t and y, and basically pass the y value off to what we just wrote, the pendulum differential equation. So it's just a little joiner function, if you like, between what we have and what we're going to need in the solver. Everything else is like we saw last class. We're going to find a constant starting value. Now notice the initial value equals two numbers, which is y1 of 0 and y2 of 0. Or, if you like, the initial position, or initial angle, and initial velocity. What you're going to be asked to do regularly here is translate. Okay, what the heck is y? Y is your position, velocity, position, velocity, position, velocity. So if I have two variables, it's position and velocity. Position is going to be negative pi over 2, and velocity is going to be 0. Let's make a quick note of that. Negative pi over 2 and 0. That's our initial position, and velocity. And what does that translate to in terms of a picture? Well, everything's in radians. So if this is theta equals 0, what we're going to be talking about is moving it up over to here. That would be negative pi over 2 for our angle. So what we're going to do is take our pendulum, swing it out to the left, and let it go with 0 velocity. So we're going to take it out and just watch it go swing back and forth. And we should see it. We can kind of expect what's going to happen. Our angle is going to be at pi over 2, and then it's going to come down. What do we expect the angle to go up to on the far side, roughly? Pi over 2, right. Except there's friction. So do we expect to quite reach pi over 2 or not? No, exactly. So it'll go almost to pi over 2, and then it'll come back, and it'll be negative something, but not quite pi over 2. And we expect to see the angle. Well, let's see what the angle does. Let's run this. The differential equation line is the solver, and this is what we get as our output. We get two curves. We plotted the y values, so one of these curves is what? Angle, and the other one is velocity. Position, velocity, exactly. So we can tell from those starting conditions, the red line is going to be our velocity because it started at 0, and the blue line is going to be our angular position. And what we see is, in fact, what we just predicted. We start at negative pi over 2, which is around 1.5, 1.6. We go up to here, which is a little lower than that, and then we see these swings gradually fade in amplitude. We can find more of this by increasing our time span to maybe 40 seconds. Those would be 40 seconds because we used units of meters, all the usual acceleration units. And there we can see the gradual diminishment because of friction in the amplitude of our pendulum's oscillations. We can also do a quick check. We could turn the friction off, make it 0, and we'd see oscillations that stayed roughly constant. But this is pretty powerful. We're actually simulating a nonlinear differential equation, which is something you couldn't do coming out of your differential equation class. This thing has no closed form solution. But MATLAB will quite happily simulate this for us, and it matches our expectations. So let me pause and just go back to the code for 1 second here, and just remind you that this line is equivalent to simulate using the DE, so using our pendulum rules, starting at y0, which is now two things, initial velocity and initial position, and simulate for the time span that was given. You define all that. You say to the solver, which is a simulator, here's my set of rules, here's how long I want you to simulate for, start and end, and here's where you're going to start the simulation in terms of velocity and position. Then let's take a little bit closer look here. What we're going to do is two different things. One of the things I want to do actually is get rid of one of the curves. So what we get is output. The interpretation of the output is key. T and y are two things, two vectors or matrices here, and it behooves us to ask what those look like. So T is going to be a vector. Y, which has two things in it, y1 and y2 in principle, is going to be a matching vector with two columns. Column here, column here. This is going to be your y1, which is your theta values, and this is going to be your y2, which are your theta prime values. And what we get is a matching. At time x, what's my position, what's my velocity? And then when we plot time against y as a whole, we get two graphs, our position graph and our velocity graph. And we can also isolate one if we want. If I just want to plot the position or the angle here, how would I change my plot command to just show the position? Angle. What would I change in this plot command? Yeah?
T versus
y1, OK. We need a couple more letters in there, but you're the right idea. How do I get the first row, first column? What do we want? Where's y1 in that big Y matrix? First column. OK. So we want the first column, which means all the rows come first, all the rows, first column only. And if we plot that, we're going to get, I just put a little close all up here. We're going to get just the position. Notice it starts at our negative 1.6, and we get decreasing amplitudes. Perfect. So we can isolate that. Now we're going to ask, what can I do with the simulation? Well, I can do thought experiments now with my simulation. And one of the thought experiments we can go through is, if I start at that same position, so here's my pendulum center, here's my mass, this is negative pi over 2. It's going to swing right now and then swing back, but always have diminishing curve, diminishing amplitude because of the friction. However, I can give it a kick. I can give it an initial velocity. I can push it down while starting in that same position, and we can see whether, well, what happens as a result of that. First of all, we want to build some expectations. If we go down to our simulation initial value, which is here, that's our initial velocity being the second component. If I make that, let's say, 1 meter per second, or sorry, 1 radian per second, that would be the units. What do I expect to have happen to this graph? I haven't run it yet. What do you? The amplitude is going to increase, absolutely, because we have more energy now, right? It's going to start off with amplitude 1.5, but it has some velocity, so it's going to go higher, and we should see values above 1.5, just as a comparison, absolutely. And when we do that, well, actually, it turns out 1 doesn't do that much, but we're actually close to 1.5. Let's give it a little bit more kick, because the friction is dragging us down here. Oh, there we go. If I give it a 2 radian, what we're actually setting here, for reference, is the slope at the start point. If you looked at that first graph, it actually had 0 slope because we had 0 velocity. The slope on this graph is your velocity. Now we've got a positive velocity to start with. And yeah, we're going further. We're going to about 1.5. So we can dial that up. Let's go up to like 5 or something. See what happens there. Oh, whoa, hello. That was weird, but totally predictable. Let me dial it back a little bit. We'll sneak up on this. Let's go to 3. 3's there. Let's try 4. 4 is an interesting one. What is happening? I've got the pendulum. I put it out here. I give it an initial kick. What's happening in this scenario? It's going around, absolutely. If I do 1 complete rotation, where am I at, radian-wise? 2 pi, which in numbers is better known as around what value? 2 pi is around 6. Hey, look at that 6.2-ish thing. So what we've counted here is zeros at the bottom, but 2 pi or 6.2-ish is also around the bottom, 6.3. And so what we've done is we've given it a kick that takes it over, but then the friction kicks in enough that it doesn't have enough angular momentum to go around the next time, and then it starts oscillating, but around 2 pi instead of around 0. So that's what we get, and we can simulate that and understand the output if we interpret this as angle against time. We can gradually dial this down if we wanted to see, well, how close can we get to just going over the top? How much kick do we need to not quite go over? And this should feel like a bisection type search, because it is. 7.5. Yeah, so around between 3.7 and 3.75 initial velocity is where we start seeing, oh, that goes too far, sorry, 3.5, 0.6. There we go. OK, this one's a nice intermediate one. 3.6 is where we get the push, and what's happening, it's hanging there. You can see the low velocity at the top there. It's going close to the top, and then it comes back, and then it does its little swing thing. So you can actually capture the motion here through the simulation by correctly interpreting the results of what you're setting as your initial values, which is, in your mind, what's happening at the start, and then what the simulation results are giving you as the output. You can now simulate the motion. You can change the starting values. You can change how long you simulate for. All that stuff's within your capability just by changing parameters in the code.